In this section, we're going to cover derivatives of inverses and logarithms. Let's do one problem number 1. They give us two functions. They give us a function f of x. Let's say that's equal to x to the 11th. Another function g of x. It's equal to the 11th root of x. And I want to know if these two are inverses of each other. They're inverses of each other if and only if I plug in g of x into f of x, if I do that, it comes out to x. And if I plug in f of x into g of x, it comes out to x. And if that's true, then these two are inverses of each other. Very simply, if I plug in f of x, I plug in g of x, which is the 11th root. Plug that into there. That's the x to the 11th power, raised to the 11th power. That comes out to x to the 1, because you just multiply the exponents here. If we do it the other way around, if we plug in x to the 11th into our g of x, that goes into our g of x, which is the 11th root of x. So that goes to x to the 11th into the 11th root. It's written like this. And that also comes out to 1. So yes, they're inverse. Are inverses. The second part of the question, part B, this is part A. Part B says the following. Part B asks you to graph f of x and g of x and show that they intersect at positive 1 and negative 1 if they intersect at 1, comma 1, and they intersect at negative 1, negative 1. Drawing the graphs, we see that they intersect at positive 1, positive 1, and negative 1, negative 1. So that's part B. I just plugged it into a graphing calculator. I used the dimensions from negative 1 to positive 1. I can use the positive 2, negative 2, but you see that it intersect at 1, 1, 1, and negative 1, negative 1. That's the graph of those two functions. You plug it into a graphing calculator. For question for part C, they asked for what is the value of the slope at 0.11 and 1. Value of the slope for the functions. They're inverses of each other, of f of x, f prime of x, and then g prime of x, and which is a slope at 1, 1, and negative 1, negative 1. First thing we do is we find the f prime, or the derivative of f prime, negative 1, and that derivative of f of x is equal to, if our f of x is x to the 11th, then our f prime of x, we bring the 11 down, x, we take away 1 from 11, so we're left with 10 up here, and that's our f prime. Our g prime, g prime of x, if our function g of x is the 11th root of x, another way to write this is x to the 1 over 11 power. That's another way to write the 11th root, a reciprocal of the actual root and the exponent. So we take away this, and we get on the top, we bring the 1/11th down, x and we take 1 away from 1 over 11. If we take away 1 from 1 over 11, we're left with, take away 11 over 11, we're left with a negative 10 over 11. And that's our g prime. I want to know the value of our prime at 1 and our value and our private negative 1. So f prime at 1 is just 11 times 1 to the 10th power, which is just 11. And our f prime at negative 1 is equal to 11 times negative 1 to the 10th power. Anytime there's an even power and there's a negative inside the parentheses, that always comes out positive. So this also comes out to 11. So at 1 it's 11, and at negative 1 it's 11. Now we do our g prime. Our g prime at 1 comes out to 1 over 11. And our g prime at negative 1 also comes out to 1 over 11, because it's still raised to the 10th power, and that power is even, so it cancels out the negative and you're left with just 1 over 11. So those are the slopes at all these different points of at 1 and negative 1 for f prime and 1 and negative 1 for g prime. Those are the values of the slope. Letter D. They want to know what is the slope of the curves, of the lines that are tangent. For both f of x and g of x. And the way the slope is at those points is your f prime around the origin. The slope at f prime of 0 gives a 0, and our g prime 0 gives a 0, which means two lines are equal 0 and y equals 0. On the x plane, remember that a line that has a 0 slope, y equals 0 is the actual y-axis. That right there is y equals 0. It is the y-axis. The x-axis is this. And that line is tangent right at the origin. So that's our x equals 0. This line, which is the axis. So x0, y0 right at the origin. If it had been somewhere else, it's different. But right at the origin, it's at 0, 0. That was number 1. Number 2 is a little bit more complicated. And why they gave us this function. Give us the function f of x is equal to 7 x cubed minus 13x squared minus 6, as long as x is greater than or equal to 1.5. And they want to find out what is the derivative of the inverse of f of x at point x 38 equals f of x 6. What this means is that when, for this function f of x, when f equals 6, the function equals 1038. And that lies within the scope of what it is. So this is the point 6 comma 1038. That's not what they're asking for. They're asking for the derivative of the inverse. The derivative of the inverse. So let's find first the derivative of the function. The derivative of f with respect to the derivative of x is equal to, if we look at this part here, we bring the 3 down times the 7. That's a 21. We take away 1 away from the 3. We're left with a 2 there. Minus 2 times 13 is 26. Take away 1 from there. We're just left with x. A constant goes to 0. Now if we plug in a 6 into the derivative, that'll give us what the slope is at x equals 6. At x equals 6, the slope is going to be 6 raised to the second power minus 26 times 6. This comes out to 756 minus 156, which comes out to 600. And that's the slope. That is the slope at d of the slope of f at 6. Now, because we're looking for the inverse would be the reciprocal. And the reciprocal would just be 1 over 600. Not the reciprocal, just the reciprocal. And that's our final answer for number 2. Number 3, we start getting into logarithms. Relatively straightforward again. Y equals ln of t to the 8th. Notice that the 8 goes with the t and not the full function ln of t. One anything about lns or natural logarithms or logs, you can take this 8 on the top and bring it to the front. So this actually becomes 8 ln of t. If we take dy dx of both sides, that's just the constant, so the 8 stays the same. We take the derivative of the ln of t, which is 1 over t. So the derivative dy dx is equal to 8 over t. Number 4, they give us y is equal to t ln of 4t squared. The way to do this particular problem is to understand there's two functions here. There's t and there's ln of 4t to the second power. So that when we take the derivative, we have to use the chain rule. You take the first, which is this one, times the derivative of the second. The derivative of the second is a little complicated. We first bring the 2 down, and we leave the inside the same. We take 1 away from there, and that's that first part. Now we take the derivative of the inside being ln of 4t. The derivative of ln of 4t is 1 over 4t times the derivative of 4t, which is 4. And that's just that part right there. First times the derivative of the second. First times the derivative of the second. Plus the second, which is ln 4t, the whole thing squared, times the derivative of the first. What's the derivative of t? Well, the derivative of t is just 1. Simplifying this, multiplying all the way across, multiplying this on the top, cancels this on the bottom. So on the bottom, on this part here, see if I got this right. Let me see. There's a t here, and there's a t here. So I'm left with, here I'm left with 2 ln 4t. That cancels, that cancels, that cancels, that cancels. I'm just left with that plus ln of 4t, take the square root of the square. Did I do this right? Yeah, I did actually. Okay, so I'm left with that. Notice in both of these, I can pull one of these. I can pull, this is a squared. I can pull a ln 4t out of both of these. So I'm left with, on the inside, if I take a ln 4t out, on the inside I'm left with 2 plus ln of 4t. And that is my dy dx. If I did this right. 4t t. That's right. That's my final answer. Let's do number 5. 5 is y is equal to ln of 6x over 6x. A lot of these problems is just the algebra, because the actual derivative portion of it is relatively straightforward. This is also a chain rule. What I did was I rearranged it a little bit. I don't like denominators, so I'm going to put this up here and raise that to the -1 power. Anything raised to the -1 power on the top actually belongs on the bottom, but I can put it on top as long as I change the sign to -1. So this is ln 6x, and this is a product rule. It's the first. If I take the derivative, it's the first times the derivative of the second, which is just 1 over 6x, and then the derivative of that, which is 6. First times the derivative of the second, plus the second, which is ln of 6x, times the derivative of the first. The derivative of the first, I'm going to bring the -1 down, leave the inside the same. Take 1 away from -1, I get -2. And then I take the derivative of 6x, which is just 6. Multiplying across this way, this 6 and this 6 cancel out right away. So here I'm left with 1 over 6x for that part right here. Plus, if I multiply all the way across, let me see, I'm actually going to put a negative in the front. Then I'm going to put a negative in the front. This minus gets multiplied through, so it's a minus ln of 6x times 6 over 6 x to the second power. We can do a little bit more simplification here. If I try to combine these two, this and this I can't combine because this is a 6x. Oh wait, when I multiply it here, 6 cancel out. This is actually 6 times 6, so this is 6x squared on the bottom. So because I can add these, this is 1 minus 6 ln of 6x over 6 squared. And that is our dy dx. dy dx is equal to 1, 6 ln 6x over x squared. Make sure I change it in my notes. Right, yeah. All right. 6x squared. Let's do number 6. Number 6 says the following. Y is equal to of 1 over. This is going to be a long one, you can tell. X plus. So we take the derivative of both sides. And the derivative of ln, it's going to look funny, but it's going to be that over 1 over x plus 7. The reason I did that is derivative of anything, that anything over 1. So I put that anything over 1. I'm going to take the derivative of this part here. What I did that was I will need to take the derivative dx of this over x times x. So how do I take the derivative of that monster? Well, I'm going to run a little bit. I'm going to bring that to the top because, again, I don't like to. So I'm going to take this, make it like this. Plus 7. I'll take that to the negative 1 power. Now I know how to do it a little bit differently. Now I know how to do it because this is just a chain rule. Take the derivative of the outside, which is 1. Leave everything on the inside the same. Plus 7. Take negative 1 away from that, so it's negative 2. Now I take the derivative of the inside. The derivative of the inside is a monster. Basically, it's the first, right, really small, hopefully it'll fit, times the derivative of the second, which is 1/2 x plus 7 to the negative 1/2 times the derivative of the inside, which is just 1. Thank goodness. Plus the second, which is, the second is x plus 7. X plus 7 times the derivative of the first, which is just x, which is just 1. So that's the derivative of this second part. That's the first part. This is that the derivative of just that piece right here. Now we plug that back into here, I'm going to rearrange this part also because that looks... start at the beginning. The derivative of y with respect to dx is equal to, I'm going to change this thing top. If I change this to the top, I multiply the top and the bottom by x over x, the square root of x plus 7 over 1. Do that to both this right here. Basically this here becomes x square root of x plus 7. That's that part right there. Now we're going to multiply it times everything that we had done before, and it is a doozy. This part is negative x square root x plus 7, close parentheses, negative 2, open parentheses, 1/2 x plus 7, negative 1/2, negative 1/2 plus see if I got this straight real quick. Okay. Plus square root of x plus 7. Plus x plus 7. Close here, and then bracket there. And close here and bracket there. Boom, 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 boom. Okay, that's so far so good. Then this part in here gets multiplied. This and this get multiplied. No. Oh, we distribute this. Distribute this outside part, and we distribute this part to this. So this becomes negative x radical x plus 7 times x radical x plus 7 negative 2 times 1/2 x in parentheses x plus 7 to the negative 1/2 plus I'll multiply this times that over there, so this becomes x square root of x plus 7 times the square root of x plus 7. I took this outside, multiplied times that, and that's what I got. I got 2. Now things start canceling out. If I look at this correctly, this part is negative x over x plus 7. It's multiplied by a negative bottom. So this becomes x plus. Notice this to the second power, which means this x plus 7. That's what it means. and I multiply this times that, and then I multiply this one more time on the bottom. I multiply this whole just did times this. That 2 on the bottom is 1. That x goes on the top. And this right here to the negative half power, this goes to the bottom. Just this right here. X 7 plus 7. 2x plus 7. This and this cancel out. So I'm left with x. Now a few things start happening. We're multiplying here, so let's get rid of this, and let's get rid of that. This, because we're multiplying that away and that goes away. One of this on the top goes away, with one of these on the bottom. So let's write down what we currently have. On the top, we're just left with 1. The bottom, we're left with 2. Times this, these two cancel out because that's just that to the second power. That cancels out, so we're left with times x plus 7. That's that pair. Plus x plus 7. And that is a very long and complicated derivative. This is as far as it can go. As far as it goes. To the next one, number 7. Number 7. Okay, this one's actually very simple, relatively simple. Number 7. Y is equal to t plus 3, t plus 7, and then t plus 5. And it gives you a clue. You can distribute all these things and make it really complicated, or you can use the properties of logarithms. Logarithm. I probably misspelled that, but you get it. Logarithm. Logarithm. The properties of logarithm, what they do is, if I take the sides, it makes this a little bit simpler. If I take the ln of y, simplify it before I actually start, and take the ln of side also, I'm allowed to do that as long as I do it to both sides. And sometimes natural logarithms, you can actually use it for something instead of just rising a bunch of logs. Some of the properties of logarithms make solving some types of problems very simple, as opposed to the long way. And this is an example of one. Because to logs, you can continue to simplify this in just logs. Whenever you're lying within the parentheses of a logarithm, you can actually do this. You can do, if you're multiplying, it's t plus 3 plus n of t plus 6 of t plus 5. Now when you take the derivative of both sides, the derivative of this is 1 over y dy dx. Take the derivative of the outside, which is ln 1 over whatever the values are, that's the derivative, 1 over that, times the derivative of what's on the y. The derivative of y is dy dx. This becomes 1 over t plus 3 plus of t is just 1, stays the same, 1, same. This becomes t plus 7. This becomes 1 over t plus. But we're not quite done. We're not y over dx. We have a y on this side. What we need to do is multiply both sides by a y. It cancels the y on this side. Multiply y on this side. But I know what y is. So our dy dx equal to y was times t plus 7 times t plus 5. Remember that's what it would be. This here. 1 over t plus 3 plus 1 over t plus 7 plus 1 over 5. That's all she wrote for number 7. Number 8. Number 8 is a doozy. Y is equal to x squared plus 7 all over x plus 4 over 3. And again, we use use the properties of logarithms to make this work out cool. Let's take the len of both sides. Len of y is equal to len of the side. Squared over x plus 4 over 3. Here we're multiplying and dividing. When you multiply, it's like adding. When you divide, it's like subtracting. So the len of y, because the len comes the len plus the len of square root of x squared plus 7 minus x plus 8 to the 4/3. Now we use another property of len, or natural logarithms. When you have a power of on the parentheses like here, and remember that this is the half power. This is the len of x, that's the same. This becomes, I can bring that half power, which is the square root, I could bring it to the front. And this becomes x squared plus 7. This I can bring this power down. I haven't done derivatives yet. I'm just working with the properties of natural logarithm. Log x plus 8. Now I can take the derivative of both sides. If I take the derivative of this, it becomes 1 over y, dy dx, to 1 over x. Here, the derivative of that is 1 over x. This becomes 1/2. What's the derivative of len of that? Well, it's the derivative of len, which is 1 over x squared plus 7. But then I have to take the derivative of the inside. The derivative of the inside is 2x. The constant goes 0. Minus 4/3, because that's constant. What's the derivative of len x plus 8? That is 1 over x plus 8 times the derivative of x plus 8. That just goes to 1, that's multiplied. So the 1 stays there, nothing happens to this part here. Let's see if we can simplify just a little bit more. 1 over x. This is 2x on the top. On the bottom, this is 2 times x squared plus 7. This becomes minus minus 4 over 3 times x plus 8. Oh man. Oh. And this is over y dy dx. Let's see the 2 cancel out here. Nothing else cancels out here. To solve for dy dx, we multiply both sides by a 1. Get rid of that side. So this becomes 1 over x plus x over x squared plus 7 minus 4 over 3 x8 plus in that bracket. We knew that y is equal to this number up here, so we just plug that in parentheses. X squared plus 7 8 raised to the 4/3 power. We wrote for that. If you multiply this through, you get even more confused. So don't do it. Don't do it, don't do it, don't do it. It'll just be painful. That's good enough. Let's do number 9. Number 9. Número 9. Y is equal to e to the 6 of t plus ln of t. Let's take the derivative of both sides. dy dt is equal to a derivative of this is just that again without changing anything. And then times the derivative of this part right here. We have to find the derivative vector t. This the derivative of this right here. Leave this the same. This is e to the 6 sine of t plus n of t. This derivative is 6. Derivative of sine is cosine of t. Derivative of t is 1, so that stays the same. And the derivative of this is 1 over t. Now I can use properties of natural logarithms to simplify it a little farther. This is enough for most problems, but there's something out here we can do with here to make it a little simpler. If we do this, sine of t times, I'm allowed to do this because I'm adding in the exponents of a natural log of the e function. I can do this, and this we've seen before. This part here, e natural log of t, that part just becomes t. This over here stays the same. This is 6 cosine of plus over t. This cancels this out, and we're left with t. 6 to 9 of t times 6 of t plus 1 over t. Now if we distribute this, take this thing on the outside, distribute it to everything on the inside. For the first part, we're going to get t e 6 sine of times 6 to the front cosine of t. That's when I distribute this to this part here. Then I'm going to distribute this to this part here. That becomes, notice what happens to t's. It's the top and it's on the bottom. So this just stays times e times 1, which is just e to the 6th sine of t. That is my dy dt. Fully simplified. Well, there is one other thing we can do. I noticed that both of these have one thing in common. This 6 e to the sine. If I pull it out, if I pull out an e 6 to the sine t, on the inside, whoops, on the inside, I pull out a sine t, e is 6 sine t, and the inside I'm left with 6 cosine of t plus 1, I believe. 6t, I'm sorry, 6t cosine of t plus the inside. That's a simpler answer, actually. Full derivative. Y dt. This in common. So I can pull it out, that on the inside. And that's a lot simpler. Number 10. Len 6y equals ey sine of 8. I'm tired. Wow. If I take the derivative, to find the derivative, I'm probably going to have to use implicit differentiation, part of it at least. And I have logarithms, so I'm probably going to use that also. So the derivative is going to look something like this. I take the derivative of this. This is 1 over 6y. And then I take the derivative of the inside, which is just 6. 6 dy dx. Notice that cancels out. And that's equal to this. These are different functions. So it's, if I take the derivative of this, this is e to the y. I take the derivative of the y, is dy dx. Wait, I'm sorry. I forgot the product rule. The product rule says what you do is you take the first, multiplying two things together. You take the first, you leave it alone, you multiply times the derivative of the second. The derivative of the second becomes cosine of 8x times the derivative of the inside of this, which is 8, plus the second one, which is sine of 8x, the derivative of the derivative of ey is just dy times the derivative of y, which is dy dx. On this side, I'm left with 1 over y, dy dx. This side, I'm left with y cosine 8x plus move that to the front. E to the y sine 8x y dx. I'm going to try to group this dy dx and that dy dx, put them on the same side. So this part becomes 1 over dy dx, 1 over y dy dx, e to the y sine 8x dy dx is equal to, that's what's left on that side, 8 y 8x. Now on this side I can pull out both this dy dx and this dy dx. I'm left with dy dx. I pull out dx. On the inside I'm left with 1 over y minus e to the y sine of x is equal to 8 dy cosine. Now what I do is I try to find a common denominator for both of these. The common denominator for both of these, if I can mix two together, it's easier. I could just take the reciprocal to solve for it. Do that is to have the same denominator. I could multiply this one by a y on the top and the y on the bottom. That means I'm multiplying it by 1. If I do that, I'm left with on the inside 1 over v1 minus y e to the y sine x. It's an old math trick. You're allowed to do that. If you notice, if you change this back, the y's cancel out, and that stays the same. But this same as there. The reason I'll do it, simplify like this, and this is still dy here. To get rid of this, I multiply by the reciprocal. So I put that to the top and that on the bottom. I multiply by both sides. So this side becomes 8 e to the y cosine x times the y is now on the top, and in the bottom I have 1 minus y e to the y sine x. I really can't simplify anymore. All I could do is I move this y to the front and put 8y e to the y cosine 8x on the top. On the bottom it's 1 minus e to the y sine 8x dy dx. Monster, 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 monster. But we are almost done. You got 11 and 12. Luckily 11 and 12 are very simple and very straightforward. Yeah, right. No, they are. These are pretty simple. 7. Almost done, almost done. Y equals 7 to the square root of s. And they're asking for dy back to dx. For us to do this problem, we have to remember the following. That if I wanted to take the general rule for this type of problem, if I want to take the derivative with respect to, let's say, x, of a constant raised to a power that has some type of value inside of it. Let's call it u. The derivative of that, that's a constant, that's a variable. It's going to be a to the u, and then ln of a times the derivative of u with respect to x. That's what we have to remember. We have to get to this when we take the derivative. So for us to take the derivative of this, dy with respect to ds, that comes same function, 7 radical s times ln of our number, our constant, which is 7 to the 11, times the derivative of the of the power of this part right here. That part right there is 1/2 s to the negative 1/2 times the derivative of s, which is ds over ds, which is just 1. Simplifying this bad boy, we get dy over ds is equal to, this stays on the top, that's still on the top. Notice what happens here. This actually means half, so the 2's on the bottom. This means raised to the negative 1/2 means this is on the bottom, the square root of s. We normally don't like square roots on the bottom. We don't like square roots on the top. It's just a math thing. So what we do is we multiply the top and the bottom by radical s. If we do that, we're left with 7 to the radical s, times radical s times the limit of 7 over 2 radical s times radical s. Again, so we multiply the top and the bottom by radical s, which we're allowed as long as we do the top and the bottom. Radical s times radical s, just s. That is the final answer. Last one, number 12. Y log base 2 of r times log base 4 of r. For this one, we have to remember a couple things. We can rewrite logs as natural logs, and then use the properties of naturals to make it a little bit simpler. Let's say we had a log to base something to something. It's going to be r. Another way to write that is we take the natural log of the variable over the natural log of the logarithm. So the natural log of a. That's how we do that. Now, if we want to take the derivative of a regular log, x of x, we're going to take the derivative of log of a to the x, comes out to 1 over x ln of a. That's what we have to remember. And we get this is because we change this into this. This is much. This version we take the derivative of this, we get this. The derivative of natural log of x is 1 over x, and that's just a constant, so that's the. Simplify first. We take the dy dr we take the first times the derivative of the second, because first, which is, I'm going to change it to natural function. First, I'm going to change it on the fly. This natural log first times the derivative of the second. The derivative of this we found to be r based on this equation. It's r natural log of 4. Plus the second, which is just ln r, times the derivative of the first. The derivative of the first we know is 1 over r ln of 2. Simplifying this, multiply, you get ln of r. Multiplying across the bottom, we get r ln of 2 times dr. That's the end of section 3.8. Hope this helps.